Okay. Thank you all for waking up on this lovely day. And, yeah, we played Tom again, right? What?
I think all the
No, no, that today Dimitri is also helping you from far away.
Oh,
Hi, Ram. Hi, Dimitri. Um, sorry for I was the last one to enter, mostly because ChatGPT was taking longer time. I think there are too many PhD students graduating or something. Anyway, welcome to Siddhant's PhD defense. Siddhant Bambri would be defending his dissertation titled The Role of Language Models in Human AI Interaction, a Critical Appraisal. His committee consists of Professor Wan Lu, Professor Dimitri Bartsakas, who is in Boston and on Zoom, and Professor Vivek Gupta, with me chairing the committee. And Tom is in attendance too. It's great to have him here. Subject to successful defense today, Siddhant plans to join Samsung Research. Of course, before we get started, as you know the drill from yesterday, I would like to say a few words about Siddhant's PhD journey here at ASU. Siddhant is a pandemic PhD student. So he talked to us in like spring or maybe fall 2019, and then he actually got admitted for fall 2020, and everything rose. And so basically, obviously, he couldn't travel. And then 2021, against all expectations, he actually managed to show up in person. And in fact, for a while, he was the only one in the lab because we were all supposed to be very worried about actually showing up for the lab. So yeah, he showed up in spring 21. So in the beginning, when he came here first, he was initially working on AI for a cybersecurity DARPA project with Adam Dupé and a bunch of folks at IBM. He was quite impressive in managing large number of people. Not everybody who starts in a fresh PhD would know what to do in team meetings, etc. And then the ability to jump into a large team project and doing good work despite the usual DARPA headaches. And in fact, a paper based on that work was published in GameSec conference, which is a pretty well-regarded conference in the intersection of AI and game theory. After that, Siddhant focused his research on understanding the role of LLMs and human AI interaction, which almost sounds reasonable, which almost sounds natural because this whole group used to be very much into human AI interaction, and we slowly were shifting into LLMs and reasoning. And so he sort of actually combines both of his dissertation combines both of those directions. He'll tell more about the actual work today in himself. His findings have been presented at multiple venues and have been cited over 800 times to date. And during his PhD, he interned at Nokia and also Microsoft Research. And I should have mentioned, I think earlier that if I didn't mention that, if he defends well today, then he'll be joining Samsung Research. So like all the best Yochanites, Siddhant was great at mentoring and collaborating with other students. He had a very fruitful collaboration, long-standing collaboration with Mudit Verma, his college mate, and he's been working more recently with Upasana, another college mate, on some really cool things. Maybe this collaboration is really just a part of Yochan chapter of Delhi Institute of Technology rather than anything else. But it was great to have. That's how the collaboration is going. In a way, I think I've seen more of Siddhant than most other Yochanites, mostly because he actually wakes up in the morning and comes to the lab early enough that he was already often here by the time I showed up. Word to the wise among you, I'm not looking at any specific people here, that if you're working with old advisors, you talk to them when they are awake, not when you are awake, by which time they are asleep. Okay. So, and he certainly has done that well. And in fact, I think that's part of the reason, I guess, he's almost making a point. 9 o'clock is my defense. And I'm happy because look, I'm great. I have a lot of energy right now at 9 o'clock. Siddhant is also a very conscientious group member. Whenever I put up some random requests on the Slack, be it asking for comments on some proposal or position paper, or asking whether or where should people go to eat. Everybody wants to eat. Nobody wants to actually call where to go to eat. Or which fall hike should we go on? Or can someone come down to pick up all these goodies? I got you. He's almost always the first to actually engage with the request on the Slack. And so it's great to actually, have that sort of a, engagement. He's also friends with all the department staff right next to us. I'm sure Monica will be heartbroken that he's graduating. He couldn't care less about the rest of the people coming and going, but she'll be very heartbroken. And then also, without getting overly specific, I would also like to mention his caring and constructive role in building 50% of a human bridge between the groups of two of his committee members with the gentle auspices of a third committee member. It's one of those if you know kind of things. Anyway, finally, if you're thinking why a guy like me who shows up in shorts and t-shirt most often is wearing this kind of a kurta that's clearly way out of my league, it's of course to avoid committing any fashion faux pas because I know he would be nattily dressed. And I didn't want, and I know I didn't want to actually commit any fashion faux pas. In fact, actually, it's one of the Shah Rukh Khan level kurtas. Shah Rukh Khan is like a great Indian actor that some of the older people know from India, that Siddhant got me. Apparently, it's part of some kind of a secret plan to up my style. All in all, it's been great having Siddhant in the lab, and I wish him success in his defense and look forward to his great career. Yeah.
Now,
Thank
before
you.
that, was it written by ChatGPT?
Which one?
This one.
You can tell, right? You can tell.
All right. Thank you so much for the kind introduction. And over the last few years, I have worked on, I mentioned the intersection of LLMs and human-AI interaction and tried gaining a critical perspective. That is my thesis now, and that is the perspective I would like to share with you in this talk today. So what is human-AI interaction we are talking about? We see examples almost daily now that we are engaging with AI systems all around us, definitely with LLMs coming in real-life applications, something as planning a itinerary for the next trip or hike or so on. And so much so that it has, the turnaround time from research to actual products has also become much quicker, such that a lot of organizations have adopted these technologies already. And so specifically, when we are looking at this human-AI interaction, just to make some terminology clear that I'll be using in this talk, we have this interaction between the robot on the left, the human on the right, and the robots. There's a sequential decision-making problem that is being considered, where the robot has a model of the problem, which we'll refer to as MR, and the human has a different model of the problem, which could be different expectations, different goals, and so on. That will get clearer with the papers that I'll mention today, which we'll refer to as MH. One of the aspects with these examples that I talked about recently that we look in human-AI interaction is the advisability aspect, where the human would, based on their model MH, would like to advise the AI agent such that it can follow that when solving a decision-making problem. Now, this advice could look like a goal-based advice, how the human would want some specific goals that the agent may not be aware of to achieve. Or it could be a plan-based advice, which is more of how the goals are being achieved. And similarly, we see some other set of examples right now, which are like Waymos, robotaxis, all these autonomous cars, where again, like humans are engaging with the AI systems on a day-to-day basis. And naturally, aspects such as safety and alignment become really critical in these scenarios. So with the help of these examples, what I'm trying to essentially say is there is another aspect of this human-AI interaction, which talks about explainability. And in this aspect, it's about the AI agent maybe expecting or getting some feedback on the plan that it is executing, or some explanations behind the agent achieving certain goals that the human will be expecting on the other side. So keeping these examples in mind, This thesis is going to focus on these two critical aspects or the umbrellas of advisability and explainability in this interaction. And more formally, I would like to introduce the kind of problems or some example problems that we are going to look at behind, which are the motivations behind all this work. For example, in goal-based advice, it could be how cognitively demanding it is for the user to give advice on certain goals. Or maybe on the plan-based advice, the user expects that the agent should faithfully be able to follow the advice that it is being given. On the explainability aspect, we can have the number of times the agent expects the user to give feedback. Maybe it is extremely cumbersome for the human to give it repeatedly. Or on the aspect of goal explanations, that are these explanations even useful or are they even sound to be given? And I'm going to touch upon each of these four different aspects. But a common underlying problem here is that there is a significant expectation of the human's time, effort, and cognitive load among all these interaction scenarios. Can LLMs actually help? So we know that large language models have been trained on huge amount of human data on the web, and they can be thought of as this collective human digital footprint. And the idea is, can these shallow and broad world models be really helpful in this kind of interaction to alleviate some of the problems humans are facing specifically? So, like I said, we will investigate this with respect to a sequential decision-making problem. And just a quick overview, we are taking the general assumptions that there's an agent which is interacting with an environment to solve a sequential decision-making problem, takes an action given any state and gets a reward from the environment. So in these different works, there will be certain assumptions on what kind of planner or the reinforcement learning agent that we have, and I'll bring that into discussion. In the first part of the talk, I'm going to talk about advisability, focusing on goal and plan-based advice. And in the second part of the talk, we'll look at plan feedback and goal explanation. But before moving further, I would like to make one additional clarification that with respect to explainability, what human AI literature actually tells, and a lot of people in this lab have actually worked on this research direction, is there is an approximation that the agent can build on the humans model, which is what we'll refer to as MHR. So the idea is that if it is not aware of the actual model, then can it approximate it in such a way that it can expect the right kind of feedback or provide explanations that are coherent with the approximate model of the human MHR. With that in mind, I'll start with the first part where we talk about seeing LLMs as a human proxy for goal-based advice. And in this case, we are going to assume that the AI agent we have is a reinforcement learning agent, and the LLM is going to serve as this human proxy, or we'll check to what extent can it actually be a human proxy in providing advice on the goals that the agent needs to achieve on behalf of the actual human user. So for context, we are looking at sparse reward reinforcement learning settings. Let us take a very quick example that there's a grid world problem where the agent has to say, pick up a key, open the door and reach the goal. Pretty simple. What the literature tells us about sparse reward is that, and how we define sparse reward, is that the agent only gets a positive reward at the end of the trajectory when it reaches the goal. And there are no other reward signals or some sort of a feedback signal during the training regime of the RL agent that it can actually help the agent to converge to the policy. So what the graph tells us is essentially the number of steps on the x-axis and the average episodic return on the y-axis. And if we just take the sparse reward setting, which is shown in the red curve, the number of steps taken for the policy to converge or plateau in this graph are much more than when we actually have shaped rewards, which are these additional reward signals that we can introduce in the learning paradigm. And past research in sparse reward RL settings has looked at how do we get these shaped rewards. It could be hand-engineered reward functions, which again the users have to, or some domain expert has to come up with, or they can even come up with expert demonstrations. So if somebody actually executes what the entire plan looks like, and efforts on the lines of imitation learning come into play. Both of which require expensive human effort. And to investigate what LLMs can do in alleviating some of this problem is we look at the Markov decision process setup, which we have in this decision-making problem, and we look at MDP abstractions. There are different kinds of abstractions, but in this work, we are restricting the scope to two. One is we can abstract the MDP, keeping the action space of the RL agent the same. So imagine if the original RL agent has stochastic transition functions, converging to the policy is even worse with the sparse reward setting. So one simplistic, one simple change that we can introduce into the MDP is make this transition function deterministic. Or something better, if we are thinking of LLMs, naturally LLMs are operating in the language space, but the RL agent is executing the actions at the lower atomic space level, where these actions may not be very interpretable to the language model that we are trying to query. So we can think of this interface, which we can call it as the abstraction in the symbolic action space, where we'll try to build this symbolic layer, essentially, that can be utilized to query the LLM to get some information on what the agent should do. So essentially treating LLM as the world model here, and try to map it down back to the RL agent or the downstream agent's action space. So I'll focus more on the second abstraction in the interest of time. And for our framework, what we essentially do is we take the state of the environment, the initial state of the environment. We query the LLM at both of these abstraction space, but specifically for the symbolic one, where we are asking the language model to give us the sub goals and the sequence of the sub goals in which they need to be achieved. Once we have this, let's call it the guide plan from the LLM on what are the sub goals that need to be achieved. We are going to use these essential sub goals essentially refer to picking up the key and opening the door. So these are more commonsensical knowledge that we are trying to derive. And that is to have like a more realistic assumption as to what the LLMs can do. Maybe they are, at least at the time, they were not really good with spatial reasoning. So even this grid world, they were not able to solve the task. Maybe there are improvements on the other side, but right now. But with the symbolic space, it's a more simple assumption to have that they can actually give us some of the guide plan. With the help of the guide plan, we construct this dense reward shaping function. And what it tells us this, that whenever the agent picks up the key or achieves any of these sub goals that the LLM told us, we'll give it some additional rewards. So utilizing from the literature what is known as the potential based reward shaping, we essentially introduce these additional rewards in the learning paradigm. And the third part of the figure is essentially the RL loop, where with these additional rewards, we are expecting if the agent can actually converge to the policy faster or not, in lesser number of steps, essentially. So the first research question we looked at is, these are essentially heuristics that we are trying to derive from the LLM. So how good are they in generating these heuristics to begin with? And how we evaluate that is the fraction of sub-goals that the agent can achieve in these different environment settings that we consider. We have the AVI environment, so the household environment, Mario, Minecraft, and each of these environments have different number of sub-goals. So that is what we try to check in the increasing order I mentioned. And we checked it with 3 different family of models at the time. So we do see that at least in certain cases, there is variable performance for sure. So there is definitely a noisy signal, but we may not achieve or get a guide plan that covers all these possible sub-goals that the agent needs to achieve. But in some cases, we do get even partial number of sub-goals. And even that information is better because earlier, if you're comparing to the baseline where we have just the sparse reward setting, the agent was not getting any other signal than when it achieves the final goal state. So coming to the more important evaluation, where we actually wanted to see did this framework of ours actually help in learning the policy faster, and that is something that we see across all the curves, where the red ones again show the sparse reward setting. The green ones are when the LLM gave us a guide plan with all the sub-goals completed and including the final goal state. And the blue one is somewhere in the middle where there was a fraction of sub-goals. So even, like I said earlier, even with a fraction of them, we could get a better signal and clearly see an improvement over the sparse reward setting. So the broad takeaway that improved sample efficiency, even with these partial plans constructed specifically using the symbolic abstraction, can be helpful in bridging the gap between what the language models can tell us, being the world model, and what the RL agent, the information at which the RL agent can actually ingest. So this covers at least one part of the advisability where we talked about goal-based advice. And moving further on the second aspect, which is the plan-based advice, this was the work that essentially treats the LLM as the planner itself. So in that case, the assumption here will be that the human wants to give some plan-based advice such that the LLM can reciprocate or see how can it transfer that advice to other queries or tasks that it is asked to perform. For this specific setting, we are going to look at the ALPHA domain, which is a text-based decision-making domain. And there are 6 categories of tasks, but one of them, for example, you pick an object, find an object in a household environment, pick it up, place it in another location of the household, and so on. And there are some very similar tasks, all of which share the same action dynamics, that pick and place 2 objects, for example. So the very similar tasks in this household setting. And for this part of the presentation, I'm going to bring your focus to this work, which was the React framework, which became essentially extremely popular at the time, and even now, among the prompting frameworks, which uses an in-context learning setup, where just to break down what React does, we have on the interleaved think tags, which is the main contribution that LLMs should be able to have these think tags, which essentially contain some reasoning trace or guidance that can help them solve this kind of tasks in this household setting. And then there are other online shopping domains as well that we look at, but I'm just keeping this example for now. So we have the think tags shown in orange. We have the reasoning traces that are part of these think tags in purple. And the overall structure of the prompting framework also includes 2 of these examples. So the expectation here is that given these 2 examples, just like other few short setting frameworks, we will have another similar task that is asked as a query, and the LLM will be able to solve that in a similar way. So our question was essentially that these decision-making tasks also have subgoal dependencies. How is it really that the LLMs, these reasoning examples that we are giving them, what part of them are actually can be attributed to the performance that we are seeing in these models? So we try to dissect the framework by performing a sensitivity analysis, looking at these 3 components of the React framework, using it as a groundwork. Is it the interleaving of the think tags that is helping it, such that, okay, we should have these think reasoning traces every once in a while during the execution trace? Or is it the content that is part of these think tags, which is the plan guidance, that is actually helping the LLM decide what are the next actions to be taken in the environment? Or the third part could be how similar these examples are that are being used, and how much dependent is the LLM on these specific examples. So we basically construct a lot of perturbation tests across each of these 3 dimensions. And for the first one, like I talked about, that these think tags have to be interleaved in the original setup. We just concatenate them upfront in the beginning of the example. And in one of the alternate variations of the same, we just anonymize the setting. So why are we doing this? Essentially, the point is that if it needs this guidance, it can be given all upfront. And even with anonymization, what we are essentially making it more general. So the idea is the results should not at least drop from the baseline, or at least should get better, ideally. And that is the expectation behind this hypothesis. For the second variation, where we look at the semantic content of these think tags, we have 4 different perturbations. We keep them in the locations that they originally are, but we replace them, maybe say, with a failure action, with a failure and an explanation, or change the ordering, and some placebo guidance, such as take a deep breath, which has absolutely no connection with what the problem looks like. And again, what is the expectation behind the hypothesis, which is straightforward, that we are definitely not giving the LLM, as per the original claims of the work, what it actually needs to take the right set of actions after these think tags. So the performance should drop again. Unsurprisingly, in a way, for 4 out of the 5 models in this case, among the OpenAI and the Claude families that we were utilizing in this period, we have the ACT and the REACT baselines towards the left and the results for both the first 2 investigations or the first 2 research questions. And we mostly see almost similar or an improvement in the performance shown by the green numbers essentially. And this is unsurprising because even with say the placebo guidance, which had nothing to do with the task at hand, the LLM actually improved the performance. So what the takeaway here was that interleaving these think tags as well as the content of these think tags was not absolutely mandatory to be the same way, or they were not essentially helpful in the LLM's performance in these cases. Which leaves us with the third question, that how do we see the similarity of the 2 examples that are being given is impacting the query at hand or the performance for the query at hand. And again, we have a bunch of variations, but I'll try to bring your focus to the last ones where the one, both, and all variations, which simply mean that if you recall, I said there are 6 different categories which again share the same action dynamics across these different tasks in this domain at least. So we have 2 pick and place task examples that are being given to the LLM to solve another pick and place problem. Let's just change one of them, or let's just change 2 of them. So if I'm teaching you how to pick and place one object, you should be able to utilize it even to pick and place 2 objects, which is just the repetition of the same thing. So we change one example, we change both. We give one example of each of the 6 categories. Now, all the information that is available about the domain has already been given now. So again, what is the expectation? The idea is that it should be, if it is generalizable enough, we should have at least similar or better performance once again, with all the information, especially with all the information being provided. However, we see an opposite trend for this third research question in this case, where the numbers completely plummet, especially for both the settings where we just changed both the examples. And we also evaluated something that is not part of the slides right now, but we also evaluated the syntactic and the semantic similarity measures between the queries that have been put as examples, as well as the queries that are actually being asked in the test domain that are available to us. And we have extremely high similarity numbers across those evaluations, and yet we see a drop in performance as soon as we change the examples. So one of the takeaways you could think is that no, this framework definitely by itself is not generalizable. But the other weight or the conjugate of this takeaway could be, if you're actually trying to exploit the in-context learning setups, maybe effort should be made in terms of finding what the right set of examples could be. So with that, I conclude the first half of the talk, which talked about where we looked at the advisability aspects, both in terms of goal and plan-based advice. And moving further, we'll look at the explainability aspect for the next 2 parts. And in the first part, we are essentially going to check if LLMs can act as a human proxy for giving this plan feedback. If I make you recall that one of the problems we discussed is these systems keep on expecting that the human has to give feedback all the time. So if LLMs can act as a reasonable human proxy, and we'll define what reasonable in this case could mean, can they, on behalf of the user, provide some of this feedback? So one of the examples that we keep in consideration here is on the type of agent behaviors. Again, a lot of these agent behaviors and the works on them have been done here, part of the lab, and I had just joined as well. So a lot of motivations actually come from there as well. And in this case, there is a robot which is at location 1 and is executing an action. As an observer, you don't know originally what the goal of the robot looks like, but is the behavior of the robot legible in this case, which means that based on the actions of the plan that you are seeing, can you accurately estimate what the goal location would look like? In this case, it's straightforward that it would be location 2, for example. But if we were to expect a similar kind of a feedback from LLMs instead of a human observer, we would want to check certain things. One is, first of all, how do lay users perform on these reasoning tasks? So specifically the theory of mind reasoning tasks in this case, where they have to answer on behalf of another observer. And this gives us a baseline performance at least. The second part is on the spectrum of where experts would give the answers and the lay users, where do LLMs actually lie? Are they closer to the domain experts, so they are extremely accurate and reliable, or they would actually look at much closer to the lay user performance, which we are still seeing what the evaluations tell us. And finally, how robust these are, because naturally, if we are to expect them to replace the human for giving some amount of feedback, we need to check for some robustness or some guarantees that we can get from this. So for the first two parts, we actually conduct an extensive human study as well. And to conduct the human study, we have these prompt setups where we describe the same thing that you saw in the video in the previous slide. We actually give it in text description, define what the expected behaviors look like to the lay users, and what the plan of the robot is. And we actually do some part of the user study even with the video demonstrations as well. And the question is, would the lay user find this plan legible and so on? So we do these evaluations across 4 different behaviors that we look at: explicability, legibility, predictability, and obfuscation. And at the time, we mostly had access to the OpenAI family of models. And the results for the lay users are shown in the purple graphs, with the y-axis showing the performance accuracy. And we essentially see that there is some reasonable performance that even both of these LLMs, or at least GPT-4 at the time, is able to get closer to the lay users, or at least there's some essence of seeing that they can perform theory of mind reasoning tasks. However, to robustly check this, we perform certain perturbation studies, and these perturbation studies have also been tested on actual theory of mind, in actual theory of mind literature, where the studies were conducted on users. So can I add some uninformative context to the problem such that the user or the human is able to ignore that context and still answer the question correctly? Or can I just, for example, in this video, it's completely blurred. Naturally, you would expect that the user is unable to answer the question. Can the LLMs also give us the same kind of performance when these perturbation tests are conducted? And taking inspiration from these examples, we introduce these additional text or context as part of the prompt, where one of them would be the uninformative context. And the expectation here would be that the LLM should not change its response in this case, because the ground truth answers still remain the same. For the other one, which is called the inconsistent belief, we would actually add this additional context where the LLM is again expected to change the response this time, because there's something like, okay, the human observer cannot even see the robot acting. So that somewhat nullifies the entire context that had been given prior to this context. And at this time in the talk, these results don't seem surprising, but clearly the performance completely plummeted based on these robustness settings, specifically for the inconsistency test, which essentially tell us that LLMs failed at these perturbation tests, but can only be regarded as approximate but faulty human proxies when we are giving these feedbacks. And naturally, more robustness testing should be done, especially in these kinds of human AI interfacing settings where we are actually trying to get AI feedback instead of the humans. But unfortunately, we don't come across a lot of these robustness tests. So that was primarily the takeaway from this study that we did. And moving forward with the last part, which is a very recent work that we actually did, and that talks about goal explanations and in the aspect of explainability. So in this setting, essentially, we are going to look at this open book question answering setup. What question, like there will be a question that the agent or this AI agent needs to answer. And open book, all it refers to is that there is a set of facts that have been given as part of the prompt or the problem that is being posed. And the answer can be retrieved from one of these facts, essentially. And for this case, we are looking at In the React setup, for example, we looked at the in-context learning or the prompting framework with these think tags. But now with the post-training techniques coming into picture, even there are reasoning models that are producing or have been trained in such a way that they produce these reasoning traces, so-called reasoning traces between these think tags before producing the final answer. So the question, the problem that at least interests us here is that if these answers generated by the reasoning models are shown to the end user, they would naturally believe, or the perception will be, that these reasoning traces are actually how the LLM or the reasoning model is coming up with the answer. So they can be mistaken for the explanation, or maybe appropriately received by it in that way. And to be an explanation, there are two aspects that we are going to talk about. One is the soundness, which will refer to if the semantics of the reasoning traces are actually present and correlated with the performance that we are seeing with the LLMs. And later on, we'll look at the second aspect, which is more on the end user interpretability aspect. But focusing first on the semantics and checking if these semantics are actually correlated with the final solution performance, we decided to create a control study setup where we have a custom SFT experiment pipeline. So what we are going to do is that if you see like there are DeepSeek R1 traces or other reasoning models that have been fine-tuned based on R1 traces, they produce traces which cannot be verified, essentially. And now we want, if you want to check the semantics of these reasoning traces, we want to make them verifiable. In order to make them verifiable, that is the whole essence or reason behind why we create these custom SFT datasets. So we divide this QA problem into two steps. Let's say the classification step and the information retrieval step. And essentially these two steps will constitute the chain of thought trace or the reasoning trace that will be part of the SFT training data, as well as what the LLM is expected to produce at the time of inference. And now that we have created these traces algorithmically, at the time of inference, if the LLM is fine-tuned in the right way, it will produce these similar traces. So we would be able to evaluate if it got the classification step correct for this problem or the information retrieval step correct in this problem. And just to make a note, these are two steps, same that at least that I chose personally, at least in this setup. You could have taken any other steps that would have been part of the trace as well. But the idea was that since we want to verify them, we will have it structured in a specific way. So for the evaluation setup, again, let's look at the prompting we look at Qwen family of models, Llama, both 1 billion as well as 8 billion results. In this case, I'll focus on the 1 billion parts right now. And to avoid any data contamination issues, at least, that could arise as questions later on, we did the prompt setup where we are just prompting the LLM to see if they have any knowledge about this kind of data sets that we are testing them. Then we have the SFT vanilla setup where we just have the input and output consisting of the problem as well as the solutions and no reasoning traces at all. The next one is with this custom SFT datasets where we have these verifiably correct reasoning traces. As an intervention study, we also have incorrect reasoning traces that have been paired with the correct solutions. And these traces have just been generated by swapping them at random in the dataset. So the problem will now has an incorrect trace, which may belong to some other problem in the training data, but has its own answer as part of the dataset. So we look at, like I mentioned earlier, we look at the final solution evaluations, and now we have access to the intermediate trace evaluations. And surprisingly, actually, in one of the three QA datasets, we saw that the SFT with incorrect traces actually outperformed the other setups. And the prompt setup is definitely the worst, but among the three SFT settings. In the other two question answering settings, we actually saw other results such that in one case, SFT correct traces was better, and in one case, even SFT vanilla was better. So there are a bunch of variations showing, giving us these takeaways that maybe having reasoning traces all the time may not be very helpful. It's not like every reasoning trace can be helpful in fine-tuning an LLM. The other observation could be even incorrect traces can actually lead to better final solution performance in this case. But one common consistent result across all three data sets that we saw is with the SFT correct trace, we got the highest numbers with the intermediate trace evaluations, which was naturally expected in some way. So that gives us a better picture as to what is really happening in terms of just using, say, the cross entropy loss for fine-tuning data, for fine-tuning experiments. We also did an error analysis, creating the confusion matrices based on, so the blue ones tell you where we use the SFT with correct trace experiments, and the red ones at the bottom show you the SFT with incorrect trace experiments for both Llama and Qwen models. And what is surprising is again the same results that I showed earlier, but much more representative with this figure, that even correct traces can lead to incorrect solutions. Incorrect traces can also lead to correct solutions and so on. And there are significant numbers that we actually see. Later on, we also did statistical testing to deny the hypothesis that semantics of these reasoning traces were not correlated essentially with the final solution. So that covers at least the first question regarding the aspect of explainability or the goal explanations that are being shown to the end users, which was on the semantics of them. The second aspect that we are going to look at, like I mentioned earlier, is the interpretability of these reasoning traces actually correlated with the final solution performance? And interpretability is a much more subjective term, so we'll try to ground it formally later on. And to be completely clear, we are referring to the end user interpretability and not mechanistic interpretability, because there are independent efforts going on in that direction. But right now, we restrict the scope with respect to the end user. So in this case, now as all we want to do is final solution evaluations. So for the experimental setup, what we can access is even fine-tuning these models with R1 traces, or let's say the summaries of these R1 traces. We also look at post hoc explanations that have been generated using prompting the LLMs and so on. So in red, we have the fine-tuning evaluations on the final solution accuracy for the R1 traces. Purple shows us the summaries, the brown shows us the explanations, and the gray ones are the custom SFT dataset experiments that we did in the previous part. So a common consistent result here is that fine-tuning with the R1 traces gave us the best performance across 3 out of the 4 models in this case, at least in terms of the final solution evaluation. And so these results just need to be kept in mind when we talk about the end user interpretability. For the end user interpretability aspect, we actually conducted a user study over 100 participants where they were shown all these 4 different kinds of traces. And we adopted the questions from the HRI literature essentially that have looked at these subjective aspects in terms of Likert scale questions, asking users to rate how predictable this text is or how comprehensible it is and so on across these different dimensions. And we also look at the cognitive load metrics and so on. And the design of the study was across the users. So in this way, the users only saw one kind of trace so that they would not confuse that, okay, maybe if they see all traces at the same time, it could actually incorporate certain biases in the evaluations. And a consistent result here, when we average the Likert scale ratings, is that the lesser we want the interpretability numbers on the upper half of the table to be higher and the cognitive load in the lower half to be lower. Exactly opposite to what R1 trace experiments tell us, that users found them to be the least interpretable across all dimensions and had the highest cognitive while understanding those traces in this case. And in fact, the custom correct traces do the best, but all the other 3 do have comparable numbers in that case. So the contrast or the trade-off that we essentially get to see is that fine-tuning the LLM with R1 traces actually gave us the best performance, if you're just concerned about that. However, that's not the same case that we want to optimize for the end users. So there is a gap that is presented by the set of results essentially. And this work is actually currently, we are presenting this at a couple of workshops in NeurIPS next week. And it's also, we got really strong reviews, positive reviews from TMLR as well. And I'm going to write the rebuttal after the defense. So some key takeaways just to recall from the work that, again, SFT within correct traces can at times even outperform the SFT with correct traces in terms of final solution accuracies. More importantly, trace correctness does not guarantee final solution performance and vice versa. And also reasoning traces that benefit LLMs don't have to be interpretable or need to benefit the end users. So that wraps up the different aspects, and especially the explainability aspect for this human interaction that I'm talking about. In terms of where I see these different directions of the research going further, in terms of goal-based advice, we are seeing agentic RL frameworks right now where LLMs are being trained in RL pipelines to all different tools, where these tools can actually act as sub-goals that need to be called at the right time during those pipelines. So we can actually look at the goal decomposition and hierarchical abstractions by treating these LLMs as the world model to incorporate in these pipelines. With respect to plan-based advice, naturally, we have come quite far from the prompting setups, more into the post-training and inference time scaling techniques. But for works that still look at in-context learning, such as DSPy is still extremely popular in certain cases. Testing these frameworks, as well as trying, maybe there can be efforts in figuring out what are some automated ways of finding the right examples to be used for every kind of problem that users may use. For plan feedback, naturally, something that I pointed out earlier, more robust user study evaluations are needed when we are trying to replace some human efforts with the users, with the AI agents. And finally, for the goal explanation part, which seems to be the most interesting to me right now, is how in the post-training regimes, we can decouple the objectives between fine-tuning the LLM to increase its performance and to actually have maybe independent efforts to construct explanations or real reasoning traces that can be shown to the end users. These have been the different research contributions that I've been fortunate and grateful to be a part of. And acknowledgements, while making this slide, it was strange because this is something that comes pretty much in the beginning of the thesis, but towards the end of the presentation. But I'm extremely thankful to, first of all, Dr. Rao. And I mean, I'm actually out of words because I rehearsed maybe the slides for this part. But I'm definitely indebted to him for enriching me in ways both professionally and personally over the last 5 years. Starting from the Zoom talks that happened during the COVID period, which was the first time I actually presented in the lab meeting, to even now to all the in-person presentations.
And you're bribing
Little bit, but and to all the other committee members for all the valuable discussions I've been able to have for my work and even outside. Been extremely grateful to have peers in my lab. These are two fall heights which cover pretty much all the people I've been fortunate to work with over these years. One was in 2021, one was in last year, 2024. The same height, the same location, different set of people. My family back in India, my partner and her cat, who have been the closest observers of my PhD journey, all the highs and lows, and my friends as well. With that, I will conclude the talk and open the floor to questions. Thank you so much.
Okay, so there's time for, this is now the public session. The committee members can ask questions anytime, but you guys also can ask questions. Yes, go ahead.
Well, the question I always ask about explanation is sort of explanation for whom or for what task. So I guess maybe looking at the last part 4. What's your prompt to the human subjects in this in the experiment in terms of what you're asking them to do?
So the prompts essentially look like we show the question, the reasoning trace, and the solution and the reasoning trace. Basically, the entire interaction that we had with the LLM generating the answer, or the R1, for example, generating the answer. And then once they have seen this interaction, specifically focusing on the reasoning trace, we explicitly point them to that these questions will be based on this part of the problem, which is the reasoning trace, and then the set of questions. So we'll ask the interpretability questions, these questions that have been listed down for each and every trace that has been looked at. Every user, there are 25 users for every trace type, and every user gets to see 5 traces. So we have 5 data points on the interpretability metrics. Towards the end of the study, we essentially adopt the NASA TLX questionnaire to ask about the cognitive load metrics. So that has been collected once at the end for every user. So that is the overall setup.
Okay, and so you're basically asking them, does this reasoning trace predict could it anticipate the next steps or conclusions based on earlier parts of it? Comprehensibility. I understood the reasoning followed by the model. I can follow next step. I was confused. The reasoning helped me understand why the model acted the way it did. Okay, yeah, that's the one we often expect users. There were no major gaps or missing steps. That, which is a hard one. I think probably the hardest to answer. You have to look at the answer and see
Yes.
and the input and say, okay, where did this part of the answer come from?
Right.
And they weren't under any time pressure, I suppose.
No, so we did estimate that we gave them actually more time than we actually estimated. And if I recall correctly, it was about 15 to 20 minutes per user participant. And the study was conducted on Prolific. Yes.
On what?
On Prolific. Yes.
Well, and then the other conclusion from this table is that all the other techniques performed kind of the same, right? And they did have the profile you expect. The interpretability scores were high and the cognitive load was low. So, what's wrong with R1 traces that leads to such a high load?
Well, there could be a couple of things actually. One natural question that yes, absolutely keeps coming is length could be a confounding factor. So naturally, R1 traces are longer than the other cases. The correct traces are actually the shortest in this case. We actually token budgeted the summaries and the explanations to about 100 tokens as well. So that is definitely a factor, but I think nobody, at least so far that we know, establishes length to be a factor that directly impacts end user interpretability as well. Maybe with respect to
that faithfulness scores would go up because everything is in there somewhere.
Absolutely. I think right. So I think the same questions that we see in terms of post training that okay, how does and there are so many efforts even people in the lab are doing that. Varying the length can actually change how the fine-tuned LLM actually performs over RL techniques or supervised fine-tuning. I think the same kind of questions and concerns can come up with users as well. So there is definitely something to be said about the length, essentially. But I mean, as domain experts, so-called, we did read the R1 traces, and they seem to be much more comprehensive in covering. There's definitely much more fluff in the context than is required just to precisely answer. So if I say that this is a 1-marker answer, that would be like a 5-marker thing that gives you example. But again, objectively being hard to evaluate, we can't really say anything much more about that.
Thank you.
Other questions?
So you said you are going to write a rebuttal, right?
Yes.
Okay, so I have a question. You said that you use the open source models,
Yes.
right? Very nice. Okay, very good. But how would you answer the question like people would like to ask you to compare with, let's say, Gemini 3? You have the results for
Right.
Qianwen and the Llama, right?
Right.
But some reviewer will ask you to say, hey, yeah, these are the old models. How about the new models?
That's true. I think that question keeps coming up with by the time the paper is in
I
review,
know.
new models come in. But
They're not reasonable, but
that's
how are you going to answer?
that's true. So one critical distinction, at least from our setup, is that definitely we are not going to be able to fine tune like a Gemini 3 scale of a model. So whatever results, we can have similar evaluations that we can ask them the same questions, conduct the user study on the traces that I haven't even played so with Gemini 3 so far, but
You don't need to, you ask her to play, right?
so they would maybe I'm sure they have some reasoning traces and we can have user study evaluations as well. So I could expect again the idea here was, at least for us, that how are these traces, what kind of traces are actually helping the model, or we try different sources, maybe the summaries, explanations, custom R1 traces, and so on. When we are specifically, like I did not mention earlier, but the focus was to look at the distillation regime, where we are trying to distill these traces and the performance from these kinds of externally acquired traces into smaller LLMs, the 1 billion and the 8 billion parameters. So the evaluation setup is definitely distinctive there. But I believe some of the R1 trace effects can still be seen with Gemini 3 if we were to use their traces as well. That is at least my expectation right now, to before I possibly do the experiment. But I'm happy to be surprised.
The closed source model doesn't give the full traces.
That's
They
another.
only give
that's
the
true.
summary of the traces. So they don't give you intermediate steps. They only give you a summary of the trace.
Right. So no, this actually that brings up one of the important observations that we had. Like towards the end of this work, we the OpenAI OSS models actually came in,
Yeah.
and they were, I think, the first set of models which clearly actually write on their website as well that they have intermediate chain of thought traces. They also have summaries or some refined version of we don't know how they are constructed and so on. And only those are shown to the end user. And they explicitly go out and say that they can be used for interpretability studies or user studies and so on. So it is kind of reaffirming our expectation that what can help the model does not really is not necessarily supposed to help the user. So that might be definitely a difficult step in evaluation with closed source. Right?
Also, I think in R1 there is a lot of incorrect steps. It's like forcing a model to give the right output. So it goes a lot of incorrect steps in intermediary, because there we use RL kind of thing to have an incorrect step, then you give a wrong reward, then it's changed territory or like these.
Mhm.
So, and that's why the length is also higher and it has a lot of incorrect steps with the correct steps. So it was expected that it will have bad interpretability because there's a lot of hanging.
Possibly, I guess, because again, like I think the challenge here was that we couldn't objectively say that with this number, this is the percentage of correctness in these traces and so on. So that was definitely a challenge, but that could have been one reason why maybe the length is bigger and so on.
Do you think of like maybe not training through SFT, but if there's any way we can take the reasoning step and train with some RL for incorrect give wrong reward or something like that? Instead of like SFT, you are training it the whole
see.
inference.
So the way I would think,
Because generally they do it like this, the RL thing also in the
right.
When they train these DeepSeek R1, and that's why there's a lot of incorrect steps also there coming
Yes.
in the output. So something like similar kind of training.
So I would think that these evaluations, but done with RL training instead of SFT.
Yes.
Right. I think if we are still running the currently known RL regime of taking outcome reward models, where we are just incentivizing, okay, if you get the final answer correct, no matter what the trace is, or at least it is difficult to evaluate the trace, we could still end up seeing similar set of results, unless we are looking at a problem which, say, a math problem or a coding problem with like an RLVR regime, where we actually can measure how correct the steps are. In those cases, maybe I can expect the results to differ, but if it's just like training these models or distilling smaller LLMs with respect to final reward being given only on the reward being given only on based on the final solution, then possibly the same expectation.
So you also try to use large language models and as a world model.
Yes, that was the first.
Have you tried to talk to young Lakun?
No, not yet at least. But
I tweet him.
Yeah, he's going to have a startup for the
I did. I did read about
for the
that.
world model thing, right?
Other questions, open session? Okay, Dimitri, do you have any questions in the open session?
No, I have a couple of questions for the closed session.
So in that case, you guys all can leave. The open session is complete. Thanks, Tom, again for your presence. Great to have you. And then the committee will still stay along with. And the recording should stop.